We are now in the second week of the course, lecture 4. So, we will start with one very important discussion, and that is the determination of degrees of freedom of mechanisms. So, there should be an S here, degrees of freedom of mechanisms. So, in today's discussion, we will stay limited to planar mechanisms only, and towards the end of the first half of the course, if some time is left in my hand, then I retain the intention of giving you a little outline, a little introduction to the spatial counterpart of this discussion. So, for planar mechanisms, the famous equation giving the degrees of freedom, known as Kurzbach equation, actually talks about only lower pairs, and planar mechanisms have only revolute and prismatic pairs as lower pairs. So the equation is this. Of course, Kurzbach might have made a lot of effort to get to this formula and formalize it, but it is actually very simple. Say n is the number of links and j is the number of pairs. What kind of pairs? R pairs and P pairs. Now we know that both revolute pair and prismatic pair give the possibility of relative motion, which is of single degree of freedom. This gives a rotation, relative rotation. This gives a relative translation. And in a plane, in general, you have x, y, theta, 3 degrees of freedom of a rigid body. So, if it leaves 1 degree of freedom, that means it imposes 2 degrees of constraints. So now you have n links in the mechanism, out of which one is anyway going to be fixed, which is the frame. So you are left with n minus 1 links which can at all move. Each of them, without any pairs, without any connections, will have 3 degrees of freedom. It can move in x, it can move in y, it can move in theta. Okay. So 3 times n minus 1, these many freedoms, all linked, all the links together have motion. Now, if there are a pairs, each of which is removing 2 degrees of freedom of relative motion, then total 2j degrees of freedom are removed. So, from these many freedoms, size n minus 1 is the movable bodies had on their own. Through the pairs, you are removing 2j of them. So the remaining degrees of freedom will be size n minus 1 minus twice j. This is as simple as that. Now, you may try to find out the relationship between the number of links and number of pairs for a mechanism which has specified degrees of freedom. So you specify the degree of freedom here and accordingly work out the relationship between n and p. Early in the development of this field, people were primarily interested in the so-called constraint mechanisms, for which there is a single degree of freedom. So for that, if you put f equal to 1 here, then you get this thing is equal to 1, and you reorganize this. You take 2j on the other side, minus 3n on the other side, and from here minus 3 goes and becomes 3 plus 3, adds up with this 1 here, becomes 4, and you have a relationship between the number of pairs and number of links. Okay. And this condition for a single degree of freedom mechanism, that is a constraint mechanism, is known as Grubler's criterion. Okay. This condition, this criterion is known as Grubler's criterion. Now, Germans write a funny character which we don't know how to pronounce correctly, and that is this U with 2 dots. This kind of vowel sounds are called umlaut. And if in normal ASCII characters, normal your keyboard characters, if you have to reproduce it, for example, in your email or in your text file, then you do not get U double dot. Then you reproduce that closest version of that sound by UE. Okay. So many Indians simply write a U and say, I don't know any better. So you can do that, but it will be little more educated stuff if you write UE. Anyway, now observe this. In a single degree of freedom mechanism, if this is going to hold as a condition between number of pairs and number of links, J and N, then in this equation, this 2J number is obviously even, 4 is obviously even, and for this condition to hold, twice N has to be even, and 3 is odd, so N has to be even. So you come to the conclusion that for a constraint mechanism, the number of links must be even. So it can be 2, 4, 6, 8 or whatever. In case of 2, actually there is nothing. It is a frame with which just one link is connected through either revolute or prismatic pair. It's an open loop mechanism, single movable link, and has 1 degree of freedom. So 2 links, 1 frame, 1 movable, and 1 degree of freedom. So that settles with the rest of the thing. Not only for constraint mechanism, for 3 degrees of freedom mechanism also you can say such a thing, because 3 is also odd. Okay. So for 3 here you will get 6 here. So for 2 degrees of freedom you will put 2 here, and therefore you will get 5 here. And in that case, this is even, this is odd, so 3n must be odd, and in that case n must be odd. So you find that for odd degree of freedom, odd number of degrees of freedom, number of links must be even, and for even number of degrees of freedom, the number of links must be odd. And this gives you a first-hand idea of what the number of degrees of freedom cannot be. For example, if you are trying to find out the number of degrees of freedom of a very complicated mechanism with lots of links and pairs, and with not only with R and P pairs, and at the end of the whole thing, if you find that it has 1 degree of freedom, it's a constraint mechanism, though the number of links was 17. So you should suspect your work, because number of links is odd, even odd 17. So the degrees of freedom must have been even. So it is unlikely that it will have 1 degree of freedom. So this is something which you can keep in mind, or getting mistakes early. Some kinds of mistakes, not all. Okay. So now we continue beyond this basic formula. Yes. Why it is jumping like this? Now you try to generalize this formula a little. Suppose there are double pairs, triple pairs also in the mechanism. So that you know how to handle them. You try to replace every double pair by two pairs, every triple pair by three pairs, and then add up the whole thing. Okay. So you take J, number of pairs, as this, where Ji is the number of pairs connecting I plus 1 links. So a simple pair, which is equivalent to one pair, okay, in the formula. So that will connect two links. A double pair will connect three links. So for three, you say add two, count that as two pairs, and so on. So this will be very simple. And use the same formula with this way. Now, if there is a higher pair, so which actually is a two-degree of freedom pair. So there we know that every higher pair in planar mechanisms can be replaced with two lower pairs and one link in between. Put those things in the formula. So if 8 higher pairs are there, then for every higher pair of that, it will operate like that. Each can be replaced at every configuration, but this is momentary, instantaneous, configuration dependent. Replaced at every configuration with two lower pairs and one additional link. So do that. So each of them will be replaced like that. So 8 additional links will come. So use n plus 8 in place of n. And for every higher pair, you are using two lower pairs. So number of pairs you count as j plus twice 8. And now simplify this. So keep this thrice n minus 1 as it is. And from here, you will get minus 3 and sorry. From here, you will get 3 8. That minus 3 has been already counted here. From here, you will get 3 8 positive. And from the second term, you will get minus 4 8. So 3h minus 4h, 1 minus h will remain. So that's it. So thrice n minus 1 from here, minus 2j from here, and 3h minus 4h gives you this extra minus h. That means whatever was the original formula, from that if you subtract h, number of higher pairs, then you will get the correct generalized formula. Now this is generalizations to include cases. Now there are some special situations that may arise for which we can modify the formula in some other ways. So in place of n, we can put n minus nr, and in place of j, we can put j minus jr. If there are nr redundant links, okay, links which are actually not doing any specific constraining task, no contribution in giving freedom or removing freedom. just unnecessarily increasing the count of the links in this calculation. They might be trying to help other links to share the load properly. That's a different thing, but not for this purpose. Not for giving or removing degrees of freedom. And if the if there is the number of associated pairs which are used to connect these redundant links to the rest of the mechanism. So if you remove that NR from the number of links and DR from the number of pairs, then you resurrect the formula again back to validity. And sometimes, even though everything looks fine, there are some extra freedoms which are actually in the book. These extra freedoms are redundant freedoms, but more modern literature typically refers to them as passive freedom, because redundant freedoms are actually used in some other context. So that is why, since the book was written at a time when they were more or less called redundant freedoms, and since I am teaching you at a time, so that FR notation has been in the book, and I have tried to keep the FR, the letter R, as in the book, so that you don't get confused regarding notation. But we call it passive freedoms. Okay. So let us see how with examples. Both these kinds of special situations and some more. Special geometry in design. Now make note that NR, JR, FR that is incorporated in the extended formula, apart from H, they are typically the result of some funny thing done in the design itself. For example, consider this mechanism: revolute, prismatic, prismatic, revolute, RPPR. According to the formula, you will get 1 degree of freedom, and a general RPPR mechanism does have 1 degree of freedom. However, by a specific kind of design, what has been done is that this slot and this slot have been aligned together. Okay, and the way these prismatic pairs are organized, even without any motion of link 2 or link 4, link 3 can actually exercise its own freedom as it wishes. Okay, just going in the 2 slots up and down. Okay, and this is a passive freedom. So if you consider link 2 as input and link 4 as output link, then there is no connection between the input and output, and the coupler link on its own is going on executing free motion, which has nothing to do with any other link. Okay, and on the other side, the degree of freedom, the useful degree of freedom, useful in the task of transferring motion from input to output, the degree of freedom is actually 0, because neither can this link rotate nor can this. Okay, because any possibility of any attempt to rotate this will try to turn this slot and misalign it with this slot, and immediately this link 3 will get blocked and it cannot move, and so this also cannot move. Independently, if you try to turn this, it will happen the same thing, because these 2 links do not have the same orientation and same length. Okay, in that case, they could actually play together. Okay. So whatever 1 degree of freedom this mechanism has nominally, that is actually wasted in this self motion of this link. Okay. So this is a case of passive freedom. And in order to remove this passive freedom from the formulation, the FR has been subtracted there. So from the formula, if you subtract FR, which is in this case 1, there is 1 passive freedom, then you get the degrees of freedom of this effective degrees of freedom of this mechanism as 0, which turns out to be the correct degrees of freedom. Now come here. Here again, the design has been so special that you get a parallelogram constructed by links 1, 2, 3, 4. And then link 5 is another rod bar of the same length as 4 and placed parallel to it and appropriately hinges. So this distance, this length, that is the distance from this pivot to this pivot on link 3 is the same as the corresponding distance on link 1. And this extension of the link 3 is taken up to that much length, which is here. So organizing all the lengths like that, you have managed this to give you 2 parallelograms connected together, making a bigger parallelogram. Now, if you take the formula as it is, how many links total? 5. 1 is frame, remaining 4. 3 into 4, 12, minus twice j. What is j? 1, 2, 3, 4, 5, 6. Twice j. So 2 into 6, 12. So 12 minus 12, 0. Degrees of freedom should be 0 here. However, there is 1 degree of freedom. You can find if you turn link 2, what happens? It turns. Link 3 goes down. Along with that, link 3 actually moves parallel to itself, and parallel to 2, 4 and 5 go down. So this parallelogram, which is a little standing halfway, it sits down and then lies down. Okay, and it can go on. Okay, so whatever motion you give to 2, that gets replicated in 4 and 5 continuously. So there is 1 degree of freedom. How did this happen? Because this link is actually functionally redundant. Okay, so if you remove that and therefore remove the pairs also, so then you get a simple 4-bar mechanism for which you know the degree of freedom to be 1. Okay. So these are the 2 things that was done in this modification of the formula: removing the redundant links, associated pairs, and passive freedoms. These are the 2 things which we have discussed. So if you do all these modifications, revisions in the formula, then you can accommodate a lot of issues in the same formulation. What remains over and beyond that is not dependent on design, but it is dependent on some special configurations that may come once in a while and see. Yes. So sometimes in some special configurations, degree of freedom formula breakdowns momentarily, temporarily, only for that configuration and nearby region. See this mechanism. Number of links I have numbered to make it convenient. One is the frame. Where is the mouse? Yes. Mouse here. So one is frame, then 2, 3, 4, 5, 6, 7, and this is the platform. So there are 8 links. One is frame, remove it, remaining 7 moving links. 7 is n minus 1. So thrice that 21 freedoms these 7 bodies might have. Now there are pairs. How many pairs? So from the frame to the platform, through every branch you get 3 pairs. So 3 into 3, 9 pairs. So 9 into 2 freedoms will go off because of these pairs. So from 21 freedoms total, 18 freedoms are gone, 3 freedoms are left. So this particular mechanism is expected to have 3 degrees of freedom. And it has, at most of the configurations, it has 3 degrees of freedom, and that is why by giving the 3 inputs at links 2, 4, and 6, you try to give inputs to those links relative to the frame because they are closer to the frame and you have ease of mounting the motors. But you could have given the inputs to some other pairs. That is, you could have mounted the motors somewhere else. Okay. So giving inputs to links 2, 4, and 6 relative to 1, you can arbitrarily position and orient link 8. 3 degrees of freedom, you use 3 degrees of freedom, you control all 3 degrees of freedom through the control near the base, through the motors near the base. So continuous motion you can have in all 3 degrees of freedom. And if you want to park the platform 8 and one particular configuration, one particular position and orientation, then you can lock all these 3 motors, 4 and 6. Okay? That is in most of the configurations, ordinary configurations. But in special configurations, what happens? What might happen? Say 1, 2, 1, 4, 1, 6. These are the input pairs. Lock them. Okay? So if you lock them, the 3 degrees of freedom are gone. And indeed, after locking them, if you consider the remaining situation as the mechanism, then you will find that 2, 4, 6 will get included in the frame. So that is one. And there will be 4 remaining links, 3, 5, 7, 8. 4 possibly movable links, not locked with the frame. So 3 into 4, 12. And how many pairs? 1, 2, 3, 4, 5, 6. 6 into 2, 12. So 12 minus 12, 0. So normal configurations, indeed, by moving, by giving inputs to pairs 1, 2, 1, 4, 1, 6, you will be able to continuously adjust, continuously monitor link 8, which is a platform, which is the output link. And wherever you want to park it, lock it. By locking those 3 inputs, you correctly get degree of freedom 0. We have seen from the formula again. However, at the present configuration in which I have tried to sketch it, notice the line of this link, the line of this link, and the line of this link are passing through a single point. So the 3 lines of links 3, 5, and 7 are concurrent. Now, between the platform and these links, what are the modes of interaction? This kind of revolute pairs, 3 of them. Now, you know that a revolute pair typically does not transmit any moment, and it transmits only forces, except for little friction and viscous effects that are there. Okay, that is, in a way, error rather than the intention. Okay, force it transmits, and And also, through constraint, it will transmit a force along this line without the inertia effects. And in order to lock the body at a particular place, you will have certainly not expect the inertia forces to pass the force in some other direction, because while your intention is locking, there will be no inertia forces. Okay, so this body, which is actually in that case a body under two forces, so the forces are equal and opposite and passing through the same line of action. Okay, so that will be this line. So this body can give any force to this platform along this line, and it will have no moment about this point, neither this force nor this force. So about this point, none of these three forces will be in a position to counter any moment. So you try to hold this platform with your hand and lightly try to turn, and it will turn. Though it was supposed to have no degree of freedom left because the three inputs are locked. So there is a transitory change in DOF, degree of freedom. There is a transitory change in degree of freedom. So at this configuration, though the mechanism should have got 0 degrees of freedom with the inputs locked and 3 degrees of freedom with inputs there. In actual fact, with inputs locked at this particular configuration, it has 1 degree of freedom. Okay, and if the inputs were operational, then it would have 4 degrees of freedom. There is a transitory gain in degree of freedom at this configuration. What is meant by 4 degrees of freedom in a plane? It means that the motion of this will not be totally in control of the three motors that you are trying to use to monitor its motion. Beyond that, any noise in the appropriate sense would damage them. In another configuration, in which perhaps this link and this link and this link could become parallel, here in a particular direction, it can execute, the platform can execute linear motion even without any motion of the inputs. That is also possible. So there is again another transitory gain in degree of freedom. There could be a transitory loss in degree of freedom also. For example, if these two links align together, then they will become so rigid that this point will not be able to move along that direction right at that instant. So that is a transitory loss of degrees of freedom, which is not given correctly by the formula. So these transitory loss and gain of degrees of freedom can happen in certain special configurations. So a configuration at which there is a transitory loss in degree of freedom is typically called a stationary configuration, and another configuration where there is a transitory gain in degree of freedom is typically called uncertainty configuration, because at that configuration the motion of the output link is uncertain. Okay. Now it is also possible to have some mechanisms where part of the design creates the possibilities of such special configurations, and when you put that mechanism in that special configuration, then sometimes it may happen that special configuration is not so localized, it may even continue in sequence of configurations, continuous configurations. So for significant amount of motion, that special situation might continue. Okay, these are typically in situations where the mechanism has been designed and put in that configuration to create trouble. I mean, typically for the time of design, at the time of design, you try to avoid such things. Okay, so that is one reason why in some designs of mechanisms you actually try to avoid highly symmetric configuration. For example, this one was one such highly symmetric configuration. Okay? Highly symmetric set of dimensions. So in order to avoid such things, you would try to break the symmetry a little at times. Okay, so I think this topic is here over, but we have quite a bit of time left in our hand for this particular lecture. So I will try to use some 10 minutes of time from this lecture hour to subsidize the next lecture and cover a little of what is otherwise, so according to subject matter, part of the next lecture. Okay. So, and that topic is number synthesis. Through this subsidy, we will ensure that the next lecture doesn't turn out to be inordinately long. So at this point, I will take a little break. You wander over this for maybe 1 minute, because the little break that I take for you will become only something like 1 minute, and I will come back and cover a little of the initial part of the next subject matter in this. So we were to um, start the discussion on number synthesis. And uh, in this discussion, in this lecture and full lecture next, we will actually stay limited to only simplest planar mechanisms, not go too deep in this. Okay. So first principle or first relationship that we will try to work out will be the minimum number of binary links in a closed chain constraint mechanism of 10 links. If the mechanism is to have, okay, so first we try to work out minimum number of binary links that must be there in a mechanism. Having perhaps other kinds of links also, perhaps not. Okay. So we denote the number of binary links as n2, number of ternary links as n3, number of quaternary links as n4, and so on. Then the total number of links in the mechanism will be like this. Okay. And if these many links are there, every binary link will have two pairs with two other links. So in each pair, each participating link will contribute to one element. The other participating link will contribute the other element of the pair. Okay. So the number of elements like this will be twice n2 plus thrice n3 plus 4 times n4 and so on, right? Because the ternary link will have 3 connections, quaternary link will have 4 connections, and so on. So equivalent simple pairs in the mechanism is this that we have already seen. Now each pair will be composed of 2 elements. So number of elements from the pair side you get as twice j, and number of elements from the linked side, binary, ternary, quaternary, etc., you get this. So these two should be equal. And we are talking about constraint mechanism, the closed-chain constraint mechanism. So Rule-Level's criterion holds. Now, what we do? We use this expression for twice j number of elements and this total number of links n here to find the condition. So this twice j is its first line, twice n2 plus thrice n3 and so on, plus up to I times n minus ni, minus thrice the total number of links n2 plus n3 plus up to ni plus 4 equal to 0. Now, as you organize this, twice n2 from here minus thrice n2 from here. So one negative n2 which we take on the other side of the equality, and so on the other side of the equality we will now have n2 and the remaining things will leave here. So this 4 has been kept to begin with here, and then thrice n3 minus thrice n3 1. 4 times n3 minus thrice 4 times n4 minus thrice n4, there is 1 n4. So you see k equal to 4, which is n4. Then 5 n5 minus 3 n5, there will be 2 n5. So for k equal to 5, it will be 2 n5 and so on. So this whole thing from n3 goes off, n2 term is here, and n4 onwards, all the rest of the terms up to ni terms, ni have been included in this sum. Okay. So this turns out to be the number of binary links which must be there in the mechanism. Okay. So 4 must be there anyway. Closed-chain constraint mechanism. Make note of that. 4 must be there anyway. And then if there is a quaternary link, then one more. If there is a pentanary link, then 2 more, and so on. So that many binary links will be there. Apparently, ternary links you can put as many as you want with no necessity to put binary links matching them in any manner, because n3 goes out of this business. So n2 min is 4. That is why the simplest basic minimum mechanism that you can think of, which has some degree of freedom and is a closed mechanism, closed chain mechanism, is a 4-bar linkage. Okay. So on other questions of number synthesis and some examples, we go further in the next lecture. Okay. So at this point, I stop and we will complete number synthesis in the next lecture.